Department of Oceanography, and I'm going to give you guys a series of lectures to prepare you for the laboratory work and the field work that you're going to be doing for the practical biogeochemistry module. We're going to start today with a lecture I've entitled Design of Experiments. So this is sort of the beginning background of everything. And I'm not sure how much work you guys have done in statistics or various types of chemistry, so I apologize if this is stuff that you know well. And I also apologize that the slides are a bit text heavy, but because we're not doing this face to face, I wanted to make sure you had all the resources you needed for going back and referring to slides and things as you start working with your own data from the field trip. So in this first lecture, I'm going to go over how to present data in significant figures and various measures of the spread of data and basic statistical analysis used in the type of data that you're going to be collecting. I'm going to talk a little bit about the difference between different types of errors that you might encounter while sampling and doing analyses. And then, of course, the great outlier question. What is an outlier and how do you get rid of it? And we'll touch briefly on certified reference materials and how they are used. So first thing to get you started, datum is a singular of the word data, which is plural. So whenever you're writing a sentence, make sure you substitute something in to make sure it's correct. So for example, the nitrate data is interesting in that it increases unexpectedly. Sounds perfectly normal, except when you take into account the fact that data is plural, the nitrate unicorns is interesting in that it increases unexpectedly obviously sounds wrong because you've used a word that sounds more like a plural. So this is something to keep in mind as you guys are writing things up and working with data. All right, significant figures. So there's basic rules for significant figures, and the easiest thing to do is just have these rules listed somewhere that you can refer to. And this is about how you report digits when you're making a measurement or doing a calculation. So any non-zero digit is significant. If a zero is between two significant figures, it's significant. To the left of non-zero digits, it's not significant unless it's also covered by the previous rule. So for rule 3, you can think of things like 0.1. The 0 is not significant. Any zero to the right of non-zero digits and to the right of a decimal point is always significant. So if I were to write a number on the board or write a number that was, let's say, 1.00, I'm indicating some meaning to you by putting that 00. I could have just written 1, but I didn't, right? So what I'm telling you is that it's not 1.01 and it's not 0.99. It's exactly 1.00, which is not the same as just saying it's 1. And then rule 5 here is basically easiest shown by an example on the next slide. Okay, so examples for each rule. So here in example 1, the number is 916.3. And so in this case, rule 1 applies where any non-zero digit is significant. So if I were to say how many significant figures are there in that number, the answer is 4, because all 4 of those digits are non-zero. For rule 2, any zero located between two significant figures is significant. So if we look at the example number 2 here, 1208.4, so that 0 in the middle is significant because it's between two other non-zero digits. So there are 5 significant figures in that number. And if we look at rule 3, any zero to the left of non-zero digits is not significant unless it's covered by rule 2. So that's looking at these zeros here. They're not significant because there's no non-zero digit to the left of them. So in example 3, there are actually only 3 significant figures in that number. So number 4, rule number 4, if you look at example number 4, 34.10, that 0 was written there for a reason. It indicates something. It's not 34.09, it's not 34.11, it's 34.10. So in this number, there are actually 4 significant figures. Now, rule 5, the one I said is best given by example. So any 0 to the right of non-zero digits and to the left of a decimal point, which is not here, covered by rule 2, may or may not be significant. So in this case, we don't know if this 0 is a placeholder or if it's actually part of the measurement. All right. And so it's very difficult. We don't actually know if this is 3 significant figures or 2 significant figures. The way you get around that when you're trying to express something precisely is to use scientific notation. So if you want that to be significant, you could say 3.40 times 10 to the minus 2. Or whoops, sorry, 10 to the 2. Okay, because in this case, by having this 0 here is significant following rule number 4. So in that case, it's 3 significant digits. So the take home, the whole reason I'm going through this is because you guys are going to do a bunch of work in the lab with standard curves, and you're going to calculate concentrations of things in seawater samples. And it's really important that you don't just spit out what your calculator gives you, or R, Python, Excel, whatever it is. You have to think about how well we actually know those numbers and what's the appropriate number of significant digits to report. Okay, so moving on to statistics. There is always going to be some type of error inherent in the analyses that you are doing. So there's some degree of uncertainty, inaccuracy, and associated error. That is not the problem. The error existing isn't the problem. The problem is, what do you do about it, right? That's the part that actually matters. It's fine that the error exists. The important thing is to estimate it, account for it, be transparent about it when reporting the data, or if needs be, reject it and try a new analysis. One of the ways that really helps you with this is measuring replicates. You never, ever, ever measure something once in the lab or collect one sample. So errors will occur. The first step in evaluating an error is to do the analysis multiple times, and you can't just throw away numbers that look different. That particularly suspect data point, the one that's different than the others, might be really useful in helping you figure out what's going wrong so that you don't waste your time by doing the wrong thing over and over. So I'll just give you an example here. So let's say you measured the nitrate concentration in seawater of a sample 6 different times, and you report your results in micromolar. So you don't just stick the average in. You start by looking at the spread, the mean, and the median. And just a quick refresher for you guys. The spread is the range. So that's basically the difference. You subtract the largest and the smallest data point for a set of measurements. So in this case, the spread, so this is the same seawater sample, right? In theory, these numbers should all be exactly the same, but they're not. There's actually a spread of 1.42 micromolar in the data. Okay, again, it's not a problem. It's about what we do with it. You also, of course, report the mean, the average of the data. So that's here. The average is 9.2 micromolar. But of course, if you just report the mean without the spread, people don't know if that mean is really a useful or accurate number. And then the last is the median. So if you have an odd number of values, then the median is the one in the middle. If you have an even number of values, you take the average of the two in the middle. And sometimes with particularly large data sets, the median can be more useful, especially if you have an outlier included. So a really large number can bias the mean, but it's not going to bias the median. And the way we typically classify experimental errors is through precision and accuracy. So precision is how reproducible the results are. So how close is each measurement to the other measurements? So how closely do they replicate one another? And this can be found by looking at the spread of the readings. This is one of the ways where the range is helpful. You can also assess this by the standard deviation, the variance, or the coefficient of variance. The accuracy on the data, on the other hand, is a different thing. Accuracy describes how close the data are to the true value or the accepted value for the measurement. Now, this is something you may never know perfectly because that implies you actually know what the true value is. And you probably don't know that with absolute certainty. And this is best described in terms of the various errors of the reading. And I think this sort of bullseye is the easiest way to help keep it straight in your mind of what precision is versus accuracy. So then the first example, everything's great. You have high accuracy and high precision. All of your samplings are very close together. That's your precision. And they've all hit the bullseye. That's your accuracy. In this example, you still have high precision. All of your measurements are really close together, which is fantastic. The only problem is they're very far away from where they're actually supposed to be. So you have very low accuracy, even though you have high precision. In this case, your precision isn't great. Your measurements aren't really falling together, but they're fairly accurate. They're all falling around the bullseye. So in this case, you have high accuracy, but low precision. And here in the last example, you don't really have very good precision. The analyses are falling all over the place and not near one another. And they're also not really clustering near the bullseye. So in this last case, you have low accuracy and low precision. The other thing to think about are various types of errors. So what's leading, what's impacting the precision and accuracy? So an indeterminate error causes a random distribution of the data around a mean point. This is frequently known as a random error, which is a sort of easier way to lead to things. And a random error leads to poor precision. So things aren't falling, your replicate measurements aren't replicating one another, and they're sort of randomly distributing. The other is the systematic error, or also known as your determinate error. And this causes all of your data to be shifted in a particular direction. Either they're all too low or they're all too high. And this leads to poor accuracy. The third type are gross errors. And these are your sort of big, crazy things that happen. There's a big mistake in the procedure and basically everything's invalid. So you've got no accuracy and no precision. So your systematic error will give you excellent precision, but everything's going to be systematically off from where it needs to be. Whereas your random error will impact your precision, but it should be randomly distributed. And it can be large or it can be small. So random errors can come from all sorts of little unpredictable variations. Sometimes they add up and cause a larger problem. Sometimes they cancel each other out. So this can be small human errors in how you're handling the equipment, fluctuations in the temperature of the room where analyses are being done. You run out of a batch of reagents, you have to use a new batch. But it should lead to a Gaussian distribution of the data. So you can account for sources of random error as long as they aren't too large. In terms of sources of systematic error, systematic errors typically are of a similar magnitude, which is why they don't impact your precision. It keeps happening over and over and over again. And this can be due to instrumental error or a method-based error or a personal error. So for example, if you don't tar the balance prior to making a measurement, or if you have a pipette that you're using but it's calibrated wrong, or you make a standard curve but you made it from the wrong concentration stock, and so everything's off by a set amount. That's what leads to systematic errors. So dealing with random errors, assuming they occur with a normal distribution, you can use statistical analyses to identify what the precision or reproducibility of your measurements are. And that's fine. It's not a problem. You just report it. Most frequently, you'll use the sample standard deviation, although sometimes if you have a really large data set, you might use the population standard deviation. And if the data are normally distributed, you can safely assume that 68% of the data will lie within one standard deviation of the mean, 95.5% within 2 standard deviations, and 99.7% within 3 standard deviations. So going back to the measurements we were looking at earlier, the sample standard deviation measures the spread of data around the mean data point for a set of replicant measurements. So here you have n as the number of measurements, so n would be 6 in this case. X bar is the average of all your x values, so it would be the average of all of your concentration values, and xi would be each individual observation. So you would take each observation minus the mean, square it, and you would sum that over all 6 of your observations, divided by 6 minus 1, which is 5. You take the square root, and that gives you your sample standard deviation. This is your population standard deviation, which again I said is very rarely used, but nevertheless it's good to know. And when you have sort of 6 replicates like this, or a fairly small number of replicates, they're going to be very similar to one another. The other useful thing is the relative standard deviation, and this is sometimes expressed as a percentage, which is the coefficient of variance. You're probably more used to seeing that, but again, this can be a useful parameter for reporting and helping someone understand, when you give them a mean value for your nitrate concentration, what that actually means, how well that measurement was made. And then the variance, which is a measure of precision, is simply the square of your standard deviation. Okay, so then if you get to outliers, So sometimes in a data set, you'll make a measurement a couple of times, and you'll get one value that's just really different than all the others. And this might be the result of a gross error. Maybe you dropped something, or you didn't realize it, but a splash of a reagent went into your sample. Do you keep that value, or do you get rid of that value? So if it's really spurious, if it's just wrong and it's from some gross error that you made, then it will skew the mean of your data and the standard deviation will be artificially high. If the point is valid and it's just somewhat unexpected, it means that your precision is a little bit lower, but if you reject it with no reason, then you're going to be introducing a bias into the data unnecessarily. And there's two ways to deal with this. There's a Q-test and a T-test. Capital T-test, not lowercase t-test like you're used to. So one option is the Dixon's Q-test, which you see a lot. You calculate a Q value, and you compare it with a table to decide to keep or reject the outlier. So in this case, you have the outlier itself, the value closest to the outlier, and then you use the range of the data, the highest and lowest data point, to calculate this Q value, and you would find a table online or in a textbook. Same idea here with the capital T-test. You have your suspect data point, your outlier, the nearest neighbor, and you use your standard deviation. So in this case, for this data set, you can see we're evaluating this outlier here. So you have 11.53 minus the nearest data point, which I think is this one, divided by the standard deviation, gives you a capital T value of this, and you would compare it to a T table. So in this case, you could say, if you look at the 99% confidence row, and n equals 7, the value we calculate is greater than this capital T value, so we can reject this outlier with 99% confidence. All right, so instead of just saying it was way out there, we got rid of it, you can say something much more scientific. The last thing are the confidence limits. This is another useful thing to report when making measurements. So this defines a range of values either side of the calculated mean. That's the sort of probability of finding the true mean. So this works with if you have normally distributed data. You would take X bar as the average of your measurements. T is the T distribution that you get from a table. So like, for example, this table, times the standard deviation divided by the square root of the number of times you made the measurement. And so in this case, you'd report the mean, 9.2, plus or minus the confidence interval. So if you use 90% probability, it's 0.4. If you go to 95% probability, it's 0.5. And again, this is a useful way for people to understand exactly how well you know the number that you measured.